Okay, we're going to take a look at multiplying and dividing non-variable radicals with square roots. Okay, this video assumes that you are very good at taking a square root and simplifying it, if it can be simplifying, and recognizing when it cannot be simplified by looking at the number underneath the radical. So you need to be very proficient at that if you're going to move forward in this video. You might want to watch a previous video to make sure that that skill is secured and have had practiced it as well. Um, Also, when we say that we're going to look at radicals with square roots, uh, it means we're only going to be looking at expressions with square roots. You may encounter later problems that have radicals of higher degree, where you're doing the third root or the fourth root or the fifth root of the radical expression. But for right now, we're just going to work with square roots, and we will address a few examples in this video. We're going to take a look at this from a steps procedure, okay? And we're going to try and follow these two steps. Step one is operate using the in within and the out without rule, and then simplify the radical. Okay, so let me give you an idea what this in within and out without rule means real quickly. Okay, it's kind of just a little phrase to help you remember the following property. If I had a root b times c root d, we would be able to operate the things that we say are in within and out without. Okay, so what does that mean? If you notice, the a and the c are both outside the radical. Similarly, b and d are inside the radical. So following that rule, it's just quite simple to say you could do a times c and then multiply that by the radical of, you guessed it, b times d. Okay? Similarly, this happens for division. If you've got a radical b, or a root b, divided by c root d, it means you can, in fact, match up the parts that are inside as well as the parts that are outside and do the operation of division. So we see that a and c are both on the outside. So that is going to give us a divided by c. And then we see the b and d are both on the inside. And that's going to give us the square root, excuse me, wrong color, the square root of b over d. Now these may look very similar, but if you think about it, what they have to do with is changing the order of operations a little bit. Just a little bit of focus on that. Here, it says that you're going to take the square root of b and then multiply that by the square root of d. This saying that you're going to take the product first, then do the square root. Okay? Similarly, for division here, it says you can have b and square root it, have d and square root it, and then perform the division. Or you can change the order and say you'll do b divided by d first, then square root that answer. Okay? So they're not actually too hard. Again, the backbone of this is being able to simplify radicals, which we showed two methods for in an earlier video. And again, I'm going to use that perfect square method for simplifying because it's faster as opposed to using the full factor tree method. If you get stuck, you need to keep working with the factor tree method until the perfect square method becomes automated. So let's move into this example. Okay, here we will try to simplify. Okay, and we have 10 root 15 over 4 root 5. So it's a division problem. Again, I'm going to match my in within and my out without. We see that 10 and 4 are both on the outer part of this. So I will do 10 divided by 4, which is just a fraction that needs to be simplified to 5 halves. And then we see the matching parts on the inside are 15 and 5, and it's division, so I can do 15 divided by 5 and call that root 3. And that is a check for doing the in within and the out without rule. And then the next is to simplify the radical. Well, if we see we've got root 3 here, which can't be simplified because it has no perfect square factors in it. It is prime. It should jump out very quickly that that is, in fact, not able to be simplified any further. So we get 5 halves times root 3 as our answer. Moving on here, again, we're going to be asked to simplify this expression, and I will do my in within and my out without rule. I notice that 2 and 9 are both on the outside, 3 and 15 are both on the inside, so I will get 2 times 9 is 18, and the square root of the product of 3 and 15 is 45. Doing these steps in this order helps me to create one radical, which is maybe a little easier to work with. Most times the number under the radical gets bigger often when I do that if it's multiplication, but the order promotes efficiency here. Sometimes you have to break the order. It's not a hard and fast rule that you have to do these steps, but it's a good model for doing them. So now I'm going to look at simplifying the radical, and 45 I'm going to look at using the perfect square method for that. So what is the biggest perfect square that goes in the 45? It's 9, so I split 45 into a product of 5 and 9. And then I will square root the 9, pull that out of the radical, and leave the 5 inside. So that means I've got 18 times 3 root 5 when I substitute that back in for root 45. So now I've got 18 times 3 to continue. Will be 30 and 24. It's 54. Root 5. Not a bad time to look at checking one of these problems on our calculator. Okay. There are no variables in it. You should be able to use your calculator to some advantage here pretty easily. So let's see what we got. I'll type the original problem, which is 2 times the square root of 3. Closing that off with that parenthesis is important. Times 9 times the square root of 15. And my calculator yields a decimal, which is fine because I'm just going to compare that to 54 times the square root of 5. And we see that these decimals are equivalent, so we can see that the first expression and the last expression are equivalent. We know that it's in fact simplified when the radical can't be simplified any further. Now that's important because sometimes you'll write an equivalent expression for this product, but you can keep simplifying the radical, which means that you're just not done. Okay, but we are done here because the square root of 5 can't be simplified any further. Okay, continuing on, we're going to look at an example that has both division and multiplication in it. Okay, so we'll simplify here. I'll try and take this in 2 steps, and you can't be overly mechanical here. You need to be able to sort of size the problem up with a little bit of a strategy here of what you will do first. Multiplication and division are somewhat interchangeable at a PEMDAS level. So the way I see it here is if I do negative 4 root 6 times 9 root 12 all divided by 2 root 3, I think I'm going to want to match up the ins of the 3 and the 12 because it'll reduce the 12 smaller than if I match the 3 with the 6. However, it does seem on the outer level that matching negative 4 with 2 is more beneficial than matching 2 with 9. Also, if I were to match negative 4 with 9, I'd be making this product larger, and maybe doing that mentally is a little bit more of a challenge. But anyway, I'm going to match the outers of the negative 4 and the 2 and the outers of the 3 and the 12. So what does this give me here? It is going to, in fact, give me um, -2 times the root 6, which I did not use in that computation, times 9. And then again, matching the inners here of 12 and 3, I will get the square root of 4, which is fabulous here because now instead of doing the in with in rule and the out with out rule, hopefully I see very quickly that I've created a perfect square, so I can continue to simplify in that regard of doing -2 times root 6 times 9 times 2. And then I can just make sure I work all the outer factors together, which in fact are -2, 9, and 2. So when I multiply that, I'll get -4 times 9 is -36. And then I will bring down my root 6, which I can't operate with anything else because it's the only radical in the expression. So if I'm looking to go in within and out without, -6 does not have another partner that would be called in this example. So we get -36 root 6 is our answer. Some people may have some awkward feeling when they go, oh, it's -36 root 6. I thought you couldn't get a negative when you're doing roots. Well, that rule is that you cannot take the square root of a negative. Okay, so the negative on the inside of the radical, such as here, the square root of the opposite of x, or -x in this case, this tends to be undefined for positive values of x. So don't confuse that with this answer, which is legit to have the opposite of a square root, or a negative square root. It's a square root of a negative that we cannot get into. Okay, so I hope this helps. Again, you want to try and work these steps. Like I said, they're not hard and fast rules, but they're a good guide. Applying that property of the in within and the out without helps try to create one radical, and then we try to simplify that radical using the perfect square method. Again, the perfect square method is where we need you to move to. If you're still doing the factor trees 2-for-1 method, as I called it in the previous video, that's good for gaining an understanding of how simplifying a radical works, but you need to move to the efficiency of simplifying them a little more quickly using the perfect square rule. So enjoy.